Okay, so let's start with our first talk after tea break. So Karan, nice to have you here.
Thanks, Paula. I also thank all the organizers for giving me chance to speak here. Yeah, so I will begin the talk with motivation behind this work. I'm a PhD scholar working in representation theory. So my guide suggested me to study representations of groups, especially finite groups, because he's working in representation theory of finite groups. Not over only the field of complex number, but also over the field of its subfields, especially the field of real numbers and the field of rational numbers. Yeah. So fortunately, we have done some work on rational representations. During the study of rational representations, we observed we can study rational group algebra in a more simplified version, which I am going to present today. So, title of the talk is a combinatorial formula for the Wedderburn decomposition of rational group algebras of metacyclic P groups. This is joint work with my PhD supervisor, Sunil Kumar Prajapati. Okay. So these are outlines. So first I will talk about, in brief, semi-simple rings and Wedderburn-Artin theorem. Then I will also talk some literature on the rational group algebras, which have been done in the recent past. After that, I will introduce my main results for finding Wedderburn decomposition of rational group algebra associated with split metacyclic P groups. I also introduce the proof in brief. During that, we will see rational representations, counting of rational representations of split metacyclic P groups also. And I will conclude my talk with generalizing our results for finding rational group algebras of ordinary metacyclic P groups. Okay. So we all know, so suppose G is a group and F a field, then we denote group algebra by Fg. This is a pre-F module with basis G, and Fg is semi-simple by Mascaz theorem if characteristic of F does not divide the order of G. So in our case, Qg is semi-simple. So this is Wedderburn-Artin theorem. It states a ring is semi-simple if and only if it is isomorphic to finite direct product of matrix rings over division rings. So I think I should write. So more precisely, we can write a ring Artinian which implies R will be some finite I equal to 1 to K Mni Di, where Di are division rings. So this result, this result was first proved by Wedderburn in 1908 for finite dimensional algebra, and of course this is a classical result in ring theory. So this result was then generalized after almost 2 decades by even Artin for all the rings which satisfy chain conditions. So in particular, if suppose R is a simple left or right Artinian ring, then R will be isomorphic to M and D. So for examples, we have illustrated here Perlis-Bacher theorem. So it tells suppose G is a finite abelian group and F be a field such that characteristic of F does not divide the order of G, then Fg is isomorphic to this expression. This is direct product over D, where D divides the order of G, F zeta D with multiplicity AD, where AD is just the number of the elements of order D of G by the degree of extension of F zeta D over F. So more precisely, if you take F equal to Q, then this AD becomes just the number of cyclic subgroups of G of order D. So of course this is a combinatorial result. For more examples, you can see this Wedderburn decomposition of some group algebras. Okay, so my first question is why the study important? So the study of Wedderburn decomposition is important because this is a classical result in ring theory, and this is also important because it is very useful to understand several algebraic structure. For example, you can see it helps to describe the automorphism groups of QG. It also helps to analyze the unit group of integral group ring ZG. So yeah, so now I will talk about literature on the Wedderburn decomposition of rational group algebra. So this is of main interest for several researchers in the recent past, and several people have done work on this Wedderburn decomposition of QG. I have listed some of them. For example, Bakshi and Kaur, Bakshi and Maheshwari, Jaspers et al, and Oltenu, and several others have done their works on rational group algebras. So one thing we have observed, so they used several complexity. For example, so they first computed all the primitive central idempotents, then using primitive central, so first they computed soda pairs. By using soda pairs, they computed primitive central idempotents. And so suppose E is a primitive central idempotent. So even you know E is a primitive central idempotent. So from going here to this MND, this is not an trivial task. This is a very difficult task. So we need many more computations, like we need to compute cross product algebra, etc. So there is complexity here. Although they also developed Wedderburn package in GAP, so we all know it fails, especially when we try to find QG of groups of higher order. So these are our motivations behind developing some formula like Perlis-Bacher theorem for abelian groups for finding Wedderburn decomposition of rational group algebra. So first, we have proved this. We have derived this formula. So suppose G is a split metacyclic P groups. Here P is an odd prime and zeta D denote a primitive dth root of unity. Then G will be generated by AB, where order of A is Pn, order of B is Pm, and the conjugacy relation BA B inverse equal to just A to the power 1 plus Pn minus S. So we have derived formula for computing the Wedderburn decomposition of rational group algebras, just depending upon these parameters N, M, and S. So I think one high school students can put this N, M, and S, and even proof involves lots of deep character theory and basic elementary theory, but to use this formula is not so difficult. So we have divided groups in two cases when N minus S is greater than or equal to M. So in this case, QG is isomorphic to Q, direct product over lambda, where lambda is running from 1 to M, Q zeta P lambda with multiplicity P lambda plus P lambda minus 1. Direct product over lambda, where lambda is running from M plus 1 to N minus S, Q zeta P lambda with multiplicity Pm. Direct product over T, where T is running from 1 to S, the matrix ring of order Pt over Q zeta Pn minus S with multiplicity Pm minus T. And for case N minus S is strictly less than M, we have again divided this case in two subcases. So suppose M equal to N minus S plus K. So for K less than or equal to S, we have this subcase 2.1, and this is the formula. For K strictly greater than S, we have this formula. So yeah, so now I will sketch the proof briefly. So what we have used to prove this result. So basically we have used deep character theory and basic elementary number theory. So first I will introduce Sood index. So this notion was defined by Sood. So yeah, so I think yesterday Digjoy talked about Frobenius Sood indicator. This is more generalized version. This notion was defined by Sood. So it tells, suppose G is a finite group and chi is an irg. My irg is the set of all irreducible characters of G. Irreducible means irreducible character over C. So and F be a subfield of C. Now we define psi. This is just the sum of Galois conjugates of chi, where Galois group is just F chi over F. So observe this is a F valued character. It does not imply this is a character corresponding to an irreducible F representation. So the smallest positive integer m, such that m psi becomes a character of an irreducible F representation, should define this notion. Later this is being called these days Schur index, and which we denote by mf chi. So here observe this mf chi times psi. This is a character corresponding to an irreducible F representation. So for P group we have nice result. So if P is an odd, then character of any irreducible representation is 1. If P is 2, then character become either 1 or 2. So to prove our results, we used this result, Rayner's result. So this is very old result. So it was proved by, so it tells, okay, suppose T is an irreducible F representation, which afford the character mf chi times psi. Then we can extend T to become an irreducible FG representation by linearly. So here A, this is a simple F algebra, and from Wedderburn Artin theorem it will be isomorphic to M and D. So Rayner's proves some properties about D. So here ZD is isomorphic to F chi, and D over ZD is just the squares of Schur index of chi over F. So yeah, so one thing we can observe here, the number of simple components in the Wedderburn decomposition of QG is equal to the number of inequivalent irreducible representation of G. So to find exactly what is the representation, we used Wegener-Mackay method. So we know this is, people call this little group method. So by using that, we explicitly compute first all irreducible matrix representation of that group, and then using some elementary number theory, we also computed character field and also counted Galois conjugacy classes of distinct sizes. So actually we need to, by observing here from Rayner's results, we need to count irreducible Q representations of distinct degree. So for that we proved this result. So suppose G is a split metacyclic P groups, then again we have, for counting of irreducible Q representation, again we have divided two cases, in two cases when n minus s is greater than or equal to m. In this case, G has one irreducible Q representation of degree P, degree 1, P lambda minus 1 times P plus 1 of degree P lambda, where lambda is varying from m to n minus s, and P m minus t many irreducible Q representations of degree P lambda, where lambda equal to n minus s plus t, and t varying from 1 to s. And again for n minus s is strictly less than n, we have two subcases, and this is the formula for counting irreducible Q representation. By using that, this is the brief idea to prove that result. So for example, we have listed some examples by using the case 1 of our main theorem. We can compute the Wedderburn decomposition of QG. One can also use Wedderga to verify this is true. It's a small group ID is 72960. So for subcase 1 of case 2, we have this example 2 and this example 3 for subcase 2 of case 2. Okay, yeah. So after that, we were willing to generalize our results in more general setting. So we have followed this classification of metacyclic P groups. Metacyclic P groups have been classified by several researchers. We followed this classification, which was given by King. He classified all metacyclic P groups into two categories. Okay, so for the first categories, it is based upon the conjugacy relation, B inverse equal to A to the power 1 plus Pn minus S. So in this case, he defined as ordinary metacyclic groups, and for case when conjugacy relation is just B inverse equal to A to the power minus 1 plus 2 to the power n minus S. In this case, he defined these classes of metacyclic groups as exceptional metacyclic groups. So one thing we can observe, all metacyclic P groups where P is an odd prime are just ordinary metacyclic groups. Even ordinary metacyclic P groups include all metacyclic P groups except a class of metacyclic group which we call exceptional metacyclic two groups. So we could handle, we could also generalize our results to compute the Wedderburn decomposition of QG for all ordinary metacyclic P groups, either it is split or non-split. So here he divided ordinary metacyclic P groups with respect to conjugacy relation and also given some restriction over R and S for a split and non-split case. So our result just tells if suppose G is an ordinary metacyclic P groups, either it is split or non-split, we can use this formula to find QG. So here again we have divided the groups in two cases. When n minus s is greater than or equal to m, then we have this formula. For n minus s is strictly less than m, we have these two subcases again. And one thing we can observe, actually I have not written here. So all the non-split metacyclic P groups falls into this subcase, and all other are split. So we have also listed some examples. So this is a group of order 256. Here you can see this is not a split metacyclic group. This is an example of non-split metacyclic 2 group. So by using our theorem, we can compute what is QG4. And one can also verify this Wedderburn components by using gap and also using Wedderburn package in gap. This is another example. So one thing, actually I have 3-4 minutes more here. So still we are remaining with this case. When G is exceptional metacyclic groups, then still we could not derive any formula to compute Wedderburn decomposition of QG. And one thing we can also observe, so we are working over that. So suppose G is a finite groups of Lie type. For example, if you take GL2 over some FQ or SL2 over some FQ, also GL3 FQ, GL4 FQ. So I think, yes, Go has proved, so Schur index of each irreducible character of these groups of Lie type, finite groups of Lie type, over Q is also 1. So if we have Schur index 1, then what is advantage for us? So advantage is because I think, yes, D over ZD, just Schur index. So if Schur index is 1, which implies D equal to just F chi. So otherwise, if Schur index is not 1, then it is difficult. So for Schur index 2, we have also derived something which is called VZ groups. This is another class of group. I am not going to tell more about that. But for Schur index greater than 1, it is very difficult because there are so many examples of division rings. But for these groups, at least, we can also derive, one can derive. We are working over that. I don't know we will be able to do or not. And one more thing we should observe here, why the study is important. Recently, Del Rio has written a series of 2 papers where he showed just the Q, suppose G and H are two finite nilpotent metacyclic groups such that this, which implies G is isomorphic to H. So one result is also here. So for any group, if you can see this will be just QG tensor QH. So if we will be able to if we will be able to derive similar formula for exceptional metacyclic groups, then these results become like a corollary by using our theorem. Okay. Yeah. So with this, okay, thank you.
Thank you. Are there any questions? Sorry.
So, yeah, I have a, firstly, it's very nice that your results are uniform in P.
Yes.
That, P comes as in a very nice way. So, whatever the decomposition, you can do it for all primes P.
Yeah, yeah.
And does this include P equals?
Yes, yes, B equal to 2 also.
Beautiful, yeah. So then, why only look at metacyclic groups? Have you looked at other P groups?
Yeah, so for other VZ P groups we have done, and that result also.
You get the same kind of behavior?
No, where we have we got like Perlis-Walker theorem result. So based upon counting of cyclic subgroups of center and cosine of center over commutator, we have derived formula.
And if you have an isoclinism class,
Yes.
is there any relationship between the Wedderburn decomposition of the stem group in that class and your group that you start?
In isoclinism, we have observed for two groups, QG may be different. Yeah, so yeah.
But is any relation?
Yes.
Because of course, abelian groups are isoclinic to the trivial groups. So,
No, even you fix the orders. Still, we have to QG is isomorphic to QH, but G is not isomorphic to H.
Are there more questions? No? Let's thank the speaker again.